Summer meetings, very brave, not leaving town. And so it's great to have everybody here tonight. We meet here at, let's see, it's room N210 of the Stewart Observatory, the lecture center here. For those of you online, we'd love to have you here in person. In addition to all of us here, we've got a nice group of folks on Zoom, members on Zoom, and also we've got some members of the public watching us on YouTube tonight. So welcome all to our meeting. Jim, are we ready to go? We're going to have a special introduction or special beginning to the presentation this evening before Tim jumps in. Our good friend David Levy, a well-known writer, observer, comet hunter, and a lover of poetry and literature, is going to open up our meeting tonight. So David, are you there? Jim is pushing a lot of buttons on the computer to see if we can make this work. Say again? David, be sure to unmute, please.
Okay, that's better. Can you all hear me?
We can hear you.
I hope it's great. My name is David, and I'm here to offer you a brief poem. I am so much looking forward to Tim's lecture tonight. It's almost as if Edward Emerson Barnard is sitting in the audience himself. And I'm really looking forward to what Tim has to say. I have two very brief poems. The first one is the Rubaiyat, which was written around 1100 by Omar Khayyam. And an English translation came in 1859 by Edward Fitzgerald. I'm going to read the first two verses of that. Wake for the sun, who scattered into flight the stars before him from the field of night, drives night along with them from heaven and strikes the Sultan's turret with a shaft of light. Before the phantom of false morning died, methought a voice within the tavern cried, when all the temple is prepared within, why nods the drowsy worshipper outside? And to respond to that, I have a brief parody by Sir Arthur Eddington, and it goes like this. Oh, leave the wise our measures to collate. One thing at least is certain, light has weight. One thing is certain and the rest debate. Light ways when near the sun do not go straight. Thank you very much, David. Welcome back, and back to you.
All righty. Before we introduce our first speaker, I do want to acknowledge the superhuman efforts of our technical team over there, Jim Knoll and Terry Lappin. And they're being assisted by Susan Knoll as well. Thanks to them, we're able to do this meeting online as well as in person tonight. So thank you all for that. In addition, they've got an extra hard job, and that's keeping me on track. This is the first time I've hosted a meeting for the TAAA. So Terry's been super helpful keeping me organized, and I'm sure she will have her work cut out for her as we go on this evening. Let me introduce our speaker tonight. Tim Hunter has been a member of the TAAA for 50 years. We just did the math. He's been an astronomer, I read, since the 50s. He's a former president of our organization. He helped start the International Dark Sky Association, now known as Dark Sky International, which I actually helped host a meeting up in Wyoming with their efforts doing dark skies last month. He's also known as a great writer. He has written several books. He writes a regular column called, wait a minute, I forgot the Sky Spy. Thank you so much. and for the Arizona Daily Star. And tonight he's talking about his newest book, which you see right up there. I'm just going to let him go from here. Thank you, Tim.
Thank you, David. Everybody hear me okay? I'm standing back over here because the slides don't show up on the viewers down there. So I'm going to be talking about the Barnard objects and basically about dark nebula. And we'll see whether this moves. Doesn't seem to want to. So I may have to get, oh, there we go. There's that same area, that introduction. This is in Perseus. And this shows Barnard 1, Barnard 2, Barnard 3, Barnard 5, and surrounding areas. You can see it's a very complex nebular region. It has both emission nebulosity, reflection nebulosity, dark nebulosity. And if you notice, you have these numbers 1, 2, 3, 4, 5 that Barnard had in his famous catalog. But then we have 205, 203, 202, 206, and 204. Well, how'd they get there? Why isn't 7, 8, 9, and 10? Well, one of the things about he had no particular scheme for choosing these things that he at least wrote. He had no particular scheme for how dark they ought to be, and he had no particular scheme for numbering. So what happened, I think, is that he would come back to a field and examine it several years later, and he wanted to mark some more, so he'd just give whatever number that was left in his catalog. So you have all these numbers in an inconsistent fashion. Now, let's see. I think I'm just going to have to go hit this is not, or stand closer. It doesn't seem to want to advance. Well, let's try the space bar here. Well, it doesn't seem to. Yeah, I don't see, doesn't seem to want to change. Well, it'll be a short talk. There you go. Okay. This is my office. This is me preparing for this talk. I don't want to embarrass myself like I've done on so many previous occasions. That's why I got the office and I make sure I get every last reference and I put it in every one of these slides. Next. This was left out of my introduction. Tim Hunter's an example of someone whose hobby has run amok, spending more time and money on it than common sense would dictate. This is actually in the biographical sketches I send out. This was edited out. All right, next slide. Well, I'm here to talk a little bit about the book, The Barnard Objects, Then and Now, that I did with myself, Jerry Dobeck, and James McGahey. Their names are kind of, or my name's kind of hidden up there. What I'm going to do is we're going to raffle off 5 books at the end of the talk. Okay, let's go on. Well, I need to introduce nebulae, and they're interstellar clouds of gas, mainly hydrogen, 99.999% hydrogen, a little bit of helium, some carbon monoxide, which turns out to be important. They're ices, like water, ammonia, and so forth, that are frozen. And there's dust. And these are all, the dust and ices are submicron size, so they're very small. These nebulae that we're going to be talking about are really vast in size, light years across. But if you're actually in the middle of one of them, it'd be almost as like you're being in a vacuum. The reason they look so dark is because such a volume, we're looking at such a large volume. Bright nebula are visible because they fluorescence. In other words, there's hot stars that are nearby, and they cause fluorescence of the molecules that are in the nebular cloud, or they reflect off particles in the cloud. So you either have reflection or emission nebulae. And dark nebulae are simply the nebulae that are silhouetted against a bright background, like a more distant star field. Next slide, please. So there's all kinds of ways of describing nebula. You can have what we call H2 regions, reflection nebula, dark nebulae, which would be the topic of this talk, supernova remnants, and planetary nebulae. Well, these are actually, the last 2 are nebula, but we're not actually in the same category. Let's go on. H1 region is just neutral atomic hydrogen. It sits there, very hard to, it's in these clouds, but very hard to pick up because it doesn't produce any signal. A molecular cloud is another term for a giant collection of gases, mainly molecular hydrogen. And the H2 region is a region of interstellar hydrogen that has been ionized. In other words, it's a proton. The spinning center has been ionized probably because of hot radiation from a nearby star. When that proton captures electrons, which are flying by all the time, it emits light. And one of the most typical wavelengths is 653 nanometers, which is in the red portion of the spectrum. And that's so-called the red hydrogen alpha areas. It emits a lot of other light, but this one is by far dominant. You go on to the next slide. So here we have M16 on the left, and that you can see the red there is mainly hydrogen alpha emission. And you can see that that is being stimulated by the star cluster, which is part of the entire complex. On the right, we have the Orion Nebula in the bottom, and we have the Running Man Nebula at the top. And you can see the complex colors. So the reddish colors are probably hydrogen alpha emission and emission fluorescence from other atoms that are there. You can see some dark nebulosity mixed in with it. And then at the top, the Running Man Nebula is mainly reflection. In other words, it's blue light that's reflecting off of ice particles and dust particles. All right, you have the next. This is a famous galaxy M82, which has tremendous star formation. And you can see all this red stuff bursting out. The areas of star formation has the very large active hydrogen alpha areas, and they produce a lot of red light. Now, there's other emissions from these areas, but the red light seems to be predominant, at least in the wavelengths that we can see and the wavelengths we normally image in. We have the next slide, please. And this is M33, and this there again, you can see those red patches. These are also areas of hydrogen alpha formation or star formation in a very active galaxy. Okay, next slide. Well, the Crab Nebula is M1, and you can see over here on the left, that is nebulosity, is fluorescing. And so the astrophysical aspects that are similar to the other nebula, but this is because it's expanding gas from the supernova explosion. And then on the right is remnants of a supernova explosion. This is a portion of the Veil Nebula, and this is being scattered. This is thousands of years ago and being scattered out and interacting with interstellar space. So we won't be talking about these. We'll be talking about the dark nebulae that are occupying the main portion of the Milky Way. Go on. And we also should mention planetary nebulae, which are also nebulae. And these are stars like our sun that are less than 3 or 4 solar masses that at the end of their life, they expand up into red giants, and shells of gas come off them, and they eventually shrink down to be a white dwarf with the expanding shells of gas, which are illuminated by the white dwarf. And it gives some really strange configurations. We've got up here M27, the Dumbbell Nebula, M57, the Ring Nebula, M76, called the Little Dumbbell Nebula, and NGC 2392, the Eskimo Nebula. There again, these are not anything to do with planets. When Herschel first looked at them, they sort of looked like they were small planets. The nebular processes are from a different than the ones we're going to be talking about, but the fluorescence and reflectance in these is a similar process. We have the next slide. So most of the nebula we're going to be talking about are called diffuse nebula. Well, nebula sort of by definition is diffuse. So the nebulae are generally extended with no defined boundaries. Occasionally there's a sharp boundary in one edge of the other, but most of the time they're not. There are emission nebulae, which I just showed, which are generally going to be in the reddish portion of the spectrum. The reflection nebulae, which is going to be a bluish portion of the spectrum, and then the dark nebulae, which is sort of our main topic. And these are shown up because they're in front of bright objects. They're in front of a star cluster, or they're in front of a whole bunch of bright stars that are further away in the Milky Way. And they're shown up by the fact that they absorb the light, and they show up by silhouetting. And the next slide, please. So here's the Lagoon Nebula, M8, on the left. And you can see in here enormous emission. This is mostly areas of emission, but see a little dark patches here and there in it. And these are areas of dark nebulosity. And some of these are actually Barnard objects. Barnard actually described them. And a few of these are what we call Bok globules, which are just small, dark nebulae that Bart Bok described. On the right, we have the Trifid Nebula, and then we can see the red emission portion of the Trifid Nebula. And you can see like a Y-shaped area of darkness in the middle of that. Barnard described that as Barnard 185. And then the bluish or greenish above it is area of reflection nebula. And this is nebulosity surrounding a cluster. Okay, we have the next slide, please. So dark nebulae are common throughout the Milky Way. They originally were felt to be holes in the Milky Way. Herschel actually felt these were holes. Until the mid-1800s, they were felt to be holes in the Milky Way. There are a number of people that just thought that they probably weren't holes, but it took a long time for that to be finally sunk in. E. Barnard, who's the main topic of this talk, and Max Wolf were the first comprehensive studies of these objects. Barnard and Wolf were friends, and they're friendly competitors. And they realized that dark nebulae are obscuring interstellar clouds of dust and gas. Okay, with the next slide. This is Barnard's picture of the Horsehead Nebula. This is actually taken in 1913, and it's a cropped and enlarged portion of a 10 by 12 inch glass plate. So the plates in those days were glass plates. They were 1/4 inch thick. They had an emulsion on one side. The emulsion faced toward the incoming light. And when they were developed, then you had black stars and white background, so quote negative. When he wanted to make publications, he would then make another plate of these and then would have a typical black on white that we're used to for publication. But when he actually examined these things as far as looking for any findings on them, he would look at the plates themselves. He described this is Barnard 33 in his catalog. He wasn't particularly interested in this. In fact, in his catalog, which we'll discuss a little bit later, he didn't actually have a picture of it. He said, I already described this object, I'm not interested in it. I don't know, and I could not find, and nobody knows where the name Horsehead Nebula came from. He actually observed this with a 40-inch refractor at Lick Observatory and found a 40-inch refractor on a dark night with good seeing was very hard to see, but he could see a little bit of shimmering light from it. All right, next. So here's a picture I took of the Grasslands Observatory, just showing a typical glass plate nebula. Now, this is not a glass plate. I just did that like that. That's what a glass plate looked like. And then if you printed it, this is what it looked like in reverse. We have the next slide. So dark nebula is extinction of light by dust and interstellar clouds. The dark nebula are often associated with giant molecular clouds. These are enormous areas, several light years across, that are mainly molecular hydrogen, but they have all kinds of other stuff in them. Small, isolated dark nebulae are called Bok globules. Bart Bok described these in the late 40s, and he thought they actually be able to be called Barnard globules, because Barnard actually had noted these, but didn't describe them specifically. The reason Bok was interested in them is they thought there might be areas of star formation. Some are and some aren't. Some of these nebulae we're discussing are star formation. Some do not have star formation in them. The dust particles we mentioned are submicron size. They're often coated with frozen carbon monoxide and nitrogen and some water too. There's also molecular hydrogen, helium, carbon sulfide, ammonia, formaldehyde, and many other entities in these things in very small amounts. We have the next slide. So E. Barnard's a really interesting person. He was probably one of the greatest visual observers of all time, certainly in the top 2 or 3. And it's ironic that his photographic talents were so good in the late 1800s that he was one of the prime people that introduced photography into astronomy and pretty much put visual astronomy out of business, even though he was a fabulous visual astronomer. And he had a number of discoveries. He discovered the 5th moon of Jupiter, Amalthea, by visual observation. Discovered the California nebula, visual observation. A number of these dark nebulae he'd actually observed before he ever photographed them. We have the next slide. So here's a picture of him at a younger age posing with the 36th inch refractor at Lick Observatory. Here he is in the middle picture with the Bruce telescope at Yerkes Observatory, and we're going to discuss that. And this is him in more maturity. Next slide. This is one of the first pictures he took at Lick Observatory. This was the lunar eclipse of January 1st, 1889. And this was near Lick Observatory. I don't think Lick Observatory was in the path, but Northern California, not far away. The director of the observatory, James Holden, had bought this portrait lens. It's 5-inch in diameter and a 30-inch focal length. It was done for portraits because of the big thing, and people would sit in the studio and use it for portraits. And he gave it to Barnard because Barnard had worked in a portrait studio for many years and had fabulous photographic talents. And Holden was aware of this and said, maybe you could take pictures of the eclipse. And they were so successful, he bought the lens and was converted into a later photographic telescope called the Crocker telescope, which Barnard used for several years at Lick Observatory. And the next slide. This is one of the first pictures of the Milky Way that he took with this Crocker lens. This is probably about a 3 degree by 3 degree area. And you see that dark area on toward the left there? Barnard never described what that was. I've looked, and I think that's Barnard 289, trying to match up all these things. He just described it, said it's within the Great Sagittarius star cloud, and didn't otherwise label it. And the next slide, please. One of Barnard's areas of expertise and what he put on the map was comet photography. He actually was the first person to discover a comet by photography. On one of his Milky Way pictures, he saw a fuzzy spot that wasn't there before, and looked at it visually the next night, and it was a comet. But Barnard, his plates were very blue sensitive, relatively speaking, and ultraviolet sensitive. And so he would pick up the ion tails of comets, which often have very dramatic action. They would be faint and not visible to the human eye. And the human eye might see the dust tail, which would be yellow or orangish, and often wasn't very active. On the left is first series of pictures of Comet Brooks in 1893, and he was the first one to have this connection of tails. Nobody ever saw this before because they couldn't see these tails. And the visual part of it didn't look all that spectacular. And a famous one I remember seeing as a small kid looking at pictures of this is 1908, it's Morehouse's comet. There again, it was unremarkable visually, third or fourth magnitude comet, but photographically was fantastic. So Barnard had many photographs, did all kinds of studies of comets photographically, and was world famous for this. He was also a very famous visual comet discoverer in his earlier days, and I think it's about 12 or 13 comets to his credit. And next slide. This is a fabulous book. William Sheehan wrote The Immortal Fire Within. This is the biography of Barnard. I highly recommend this. This is really a good read, even though you sort of know what's going to happen. It's amazing what kind of life this guy. He was born in 1857 in Nashville. He lived during the Civil War, was impoverished, worked in a photographic shop, barely making any wages. By his visual comet discoveries as a young man, a teenager and a young adult, when Vanderbilt University got established, was able to go in their astronomy department and become one of their observers. He was so famous for his comet discoveries, that he was employed by Lick Observatory and opened in 1879. And then he went on to Yerkes Observatory for the rest of his career. We have the next picture. Max Wolf was a contemporary of Barnard's. We have the next picture. And he lived in Heidelberg, Germany. And this is the Bruce telescope in Heidelberg, Germany. It's a twin 16-inch refractor. There are 3 Bruce telescopes, and I'll have a little slide that shows them. He used this telescope mainly to photographically search for asteroids. He also took pictures of dark nebulae and didn't do anywhere near the extensive work that Barnard did, but he did quite a bit of extensive work. And it was a competitor for discovering asteroids and occasional comets. Next picture. So this is an interesting slide. On the left here, you can sort of see the center star, a little fuzziness around it. This is actually a reflection nebula. It's a Vandenberg object nowadays. And you can see up from the left, there's a little area sort of darkness there. And this was discovered in 1905 by a contemporary of Max Wolf. And this was with one of the Bruce telescopes, 16-inch telescope. And the field of view of this telescope is probably about 4 or 5 degrees. On the right is a picture with a 28-inch reflector at Heidelberg that Max Wolf took of this thing. It's now called Barnard 175. Barnard was very contentious. He claimed that he actually had observed this and photographed it earlier than this, but he never bothered to publish it. So the credit for this is given to Max Wolf. The next slide. This is what that looks like with a 20-inch telescope. So you can see, if you're looking at that with color imaging and modern imaging, you would not expect that would not be a hole in the sky. You would know that there's got to be dust or something in there. But of course, Barnard didn't have access to color imaging, and his plates were insensitive to blue insensitive to red and the orange portion of the spectrum. We have the next slide. Well, Catherine Wolfe Bruce is a very interesting person. She lived from 1816 to 1900. She was a very famous patroness of astronomy. Her father had done a printing type, and made a fortune. And she inherited that. She gave donations to Harvard College Observatory, the University of Chicago, which owned Yerkes, and Heidelberg, Germany, for research telescopes. These are the Bruce telescopes. The only one that's still in existence is the Bruce telescope at Heidelberg. Barnard used one of these telescopes to produce an atlas of selected regions of the Milky Way. And she gave money for the Bruce Medal, the Astronomical Society of the Pacific, which is still being awarded. And that's considered one of the most prestigious awards in all of astronomy, because this is given for somebody for a lifetime worth of work in astronomy. We have the next slide. Here's a picture supposedly of her. I took off the internet. I read that this probably is not a picture of her. She was a real recluse. And I says, who knows where this came from? That is a picture of her father, though. We have the next slide. So in 1897, she was convinced to give Barnard of the University of Chicago, which is Yerkes, $7,000 for the photographic telescope. That was a fortune in those days. That's probably, I don't know what the estimate that nowadays, but in hundreds of thousands of dollars nowadays. This had a 5-inch guiding telescope and 2 photographic doublets, 10-inch and 6¼ inch. Next slide. Brasher made a special 10-inch lens, 50.3-inch focal length, so an f5 basically. There was a 6.5-inch commercially purchased lens from Voigtlander, which is a company making lenses those days. And that had a 31-inch focal length. And it's used usually for whatever reasons referred to the 6¼ inch lens. And then Brasher completed all this in September 1900. Next slide. So here's what we have. And I don't have I have a pointer, but I'm not sure the people in the Zoom can think of. So that right there, where move the mouse to the left, down, that right there, the bottom telescope. Yeah, oops, here, maybe I can move the mouse. That is the 6¼ inch telescope. The big one in front is the 10-inch, and the one that Barnard's sort of looking through is a 5-inch guiding refractor. Then he often put what he called magic lantern lenses or slide lenses on for small, very wide field imaging. So we do all those. This is a picture of the telescope sitting in a hallway in Yerkes Observatory. I think we have the next slide. So the photographic Bruce telescope at Yerkes was in a wooden building that was 15 by 33 feet in length, east and west, had a 15-foot dome with a 4-inch wide opening, so we didn't have to move the dome very often. Had a very heavy pier. The pier was bent to form polyaxis, so the telescope swung under the pier. The pier and mount were made by Warner and Swayze with a pendulum cock drive. Well, to get all this instrument done, this didn't get all finished and placed in position at Yerkes until April 1904. And the next slide. The 10-inch doublet, which is crowned in flinch glass, that was the Bashir figure lens. Barnard's had exquisite definition over a 7-degree field and pretty good over a 9-degree definition. And the 10-inch doublet used 12 by 12-inch photographic plates, and these are about a 1/4 inch thick, and you can actually take them and flex them. They're fairly tough, but if you'd fiddle with them too much, you'd break them. And the 6¼ inch doublet used 8 by 10-inch photographic plates. It was mainly used to take the same field and to make sure whatever you claimed was on the big plates was there, so that you could double check yourself. Next slide. So Barnard received the grant from Mr. John Hooker of Hooker telescope fame. Hooker gave money for the 100-inch mirror at Mount Wilson. He got money from Hooker to spend the spring and summer in 1905 bringing his telescope to Mount Wilson from Yerkes Observatory. The Yerkes Bruce telescope was transported to Mount Wilson, installed in a temporary wooden structure from February until September 1905. And Barnard would sit there and guide the telescope all night long, and exposures were anywhere from 2 to 8 or 10 hours, manually guided exposures. And you'd hear the cougars growling in the background. You can imagine, it was very primitive in those days, no light pollution. And next slide. The object was for him to obtain the best possible photographs of the Milky Way. 154 plates were obtained with a 10-inch doublet, and 151 plates were obtained with a 6¼ inch doublet simultaneously. So he would photograph all night long and then immediately go to the darkroom the next morning and then spend another several hours examining things. So he hardly ever slept. Just amazing. And the next slide. So here's the Bruce telescope set up Yerkes on the left. And here's in the temporary building on Mount Wilson on the right. He was the only one on the mountain at night. The observatory wasn't there then. It was just a trail up there in this wooden building. Next. So there, he published his original list of dark nebulae in 1919, 182 of them. This is considered a classic work. And he numbered it 1 to 175. And then he had 44A, 67A, 83A, 84A, 117A, 119A, 131A. So there's 182 total. And I don't know why he had these A's, because I'm nowhere near M44. 44A is nowhere near 44. Maybe he would just decided he didn't want to put a different number, didn't want to call it 45, so he just put that number. I can't figure out how he got these numbers. Anyway, there are 182 of these. Next slide. He wanted to have a photographic atlas of the Milky Way. He was working on that. The atlas was secured by a grant from the Carnegie Institution in 1907. So he had all this money for this thing. But that was delayed because he had a 1913 publication, which had been delayed about 15 years, for celestial photography from the Lake Observatory in 1889, 1905. He didn't get around to getting that published until 1913, mainly because he was dissatisfied how the prints demonstrated his photographic work. And he would constantly argue with the printers and wouldn't accept it. And he would put it off. And he wanted to give even the money back for the Lick publication. He was finally decided to publish the Lick publication. Then he finally got around to going after his photographic atlas of the Milky Way. Next slide. So he, in 1915, 1917, selected 35,000 photographic prints, actually photographic prints. They're basically 9 by 9, needed for the publication of 700 copies of the atlas, each of which contained the photographic prints. So this book that was printed actually had the photographic prints in the book. And he selected every single one of those. And he would go from Yerkes Observatory, which is on Lake Geneva, in southern part of Wisconsin, actually Williams Bay, and would take a train all the way down to Chicago to look at these things periodically. Well, not until 1922 was the first draft of the photography descriptions completed, but he was ill and could no longer work, and he died the following year. And next slide. So Edwin Frost, here on the left, who was the director of Yerkes Observatory, and Barnard's niece, Mary Calvert, right there, looking through a 12-inch refractor, they got together and completed his work. Mary Calvert worked for Yerkes as sort of an assistant, and she was actually Barnard's niece, an assistant. We have the next slide. So after Barnard's death, the prime examples of photographs were published in 1927, and it's now called Photographic Atlas of Selected Regions of the Milky Way, because he didn't cover the entire Milky Way, just selected regions, so they changed the title. Frost and Mary Calvert were the ones that put it together. They had a second list that had been started by Barnard before his death. This list is started at number 201 and ended at 370, but there are no Barnard objects 176 to 200. For some reason, they didn't number them. I never quite understood that. 700 copies of the atlas are printed in 1927. It's an incredibly valuable book if you get a hands on one of them. I think it's worth $30,000 to $50,000. Next slide. So the atlas is composed of 2 volumes. Part 1 is the photographs and descriptions. There's 52 original prints, because there are a couple other extra prints from Barnard's negatives or plates. And part 2 is the charts and tables that show the objects of interest in the plates. So next slide. So if you want to look at these, the Georgia Institute of Technology has a website that has this book on. I use this website all the time. It's fantastic. And the person who put this together is apparently a distant relative of, he's the head of the astronomy department, a distant relative of Barnard. Jerry Dobeck, my buddy, published a reprint of this from Cambridge University Press in 2011. Let's go ahead and the next slide, please. And this is a photographic atlas selected region of the Milky Way. This is a wonderful book. I recommend people get this. I think it's available for not too expensive on the used market. There again, you get all the time. Next slide. So the Barnard objects are important because they're important from a historical point of view. They seem arbitrary and there are multiple dark areas he didn't catalog. Right next to areas he cataloged. In fact, some of the pictures I've taken, they look darker. So why do you look at this area? Who knows? There are areas of intense study today because they're regions of star formation and potential star formation. And next slide. So here's Barnard's plate 1. This is Lydia and his atlas. You can see what's centered. Anybody recognize what that's centered on? Double cluster. So he has the double cluster. And you can see that Mary Calvert made a chart of this and drew on it. And you can see over maybe to the right of the double cluster on both the plate and the chart, a little darker. That's Barnard 201. So I'm thinking, well, you had plate number 1 in your atlas, but you have Barnard number 201 is the first one in the plates. Next slide. Here he did plate number 4 is the Pleiades. He was one of the first to understand the extensive nebulosity around the Pleiades. And he actually had an article that was done earlier where he described 100 square degrees of nebulosity around the Pleiades and had drawings of it in long exposure. This is a 4-hour exposure. He took exposures up to 15 hours of that. So he do it over 2 nights. And this is the chart in there. Now, this is all nice, but there's no Barnard object on this. So he just put that in to show it. Why? I don't know. Well, of course, this was done posthumously, so I think they just sort of glad his papers together to put it together. We have the next slide. This is the M24. M24 is actually the small Sagittarius star cloud, as originally described by Messier. Barnard was fascinated by this area. So there's his plate of it, and there's the drawing on the right of Mary Calvert and the Barnard objects on that. Next slide. Well, I got interested in doing all these Barnard objects. I wanted to photograph them all, and I wanted to do all in color. This was a fair amount of work, and it led to the book, The Barnard Objects Then and Now, which we'll be raffling off a few copies of. Available from Amazon and Springer. Any good bookstore should have it, I hope. Anyway, next slide, please. So the book has a foreword by William Sheehan, who wrote the biography of Barnard. So I'm extremely proud that he agreed to do it. There's overview of nebulae, which basically you just saw. But one of the things I think the book offers, which I have not seen anywhere else because it's so frustrating, I have an overview of astronomy catalogs in there, fairly extensive chapter on the various catalogs out, because in all their various abbreviations, because you see these old time, what does that mean? Where'd that come from? What is that? You know, and people will introduce these terms and then won't define them. And the other thing is they'll sometimes capitalize them, sometimes not capitalize them, sometimes put a space between the catalog name and the number and not put a space between it. It's very frustrating. So I want all that in there. Then I talk about Barnard and the actual photography that he did. What did he do? How did he work in the darkroom? In my earlier days, I was an amateur photographer and my results were anywhere from mediocre to extremely poor. But I understand darkroom procedures. And so I can understand when Barnard write articles about darkroom. I can remember all my miserable times in the darkroom, spilling chemicals, getting holes in my pants, producing things that had thumbprints on them, and so on and so forth. I can understand. And so I discuss that. And then we go on to chapters of visual. A lot of these are good visual objects. Then discuss the modern imaging of them, which is sort of what this is talking about. Some pictures of selected ones. And then I'm going to talk a little bit about the missing Barnard objects. And then where are they now? What are we doing with them now? And then one thing I am proud of, I have a pretty extensive glossary. Any term that I looked at that I didn't understand, they put in the glossary. So somebody could look it up. And then we have a table of the Barnard objects. The next slide. So how did he image these Barnard objects? Well, I won't go through these slides. Basically, the wide field imaging with a full frame 36 by 24 millimeter camera. And we did long focal length imaging. Long focal length imaging was done with a 24-inch telescope or 20-inch telescope. The wide angle was done generally with a Takahashi Epsilon 180 f2 telescope, which gives a 500 millimeter focal length and it gives a 4.1 by 2.7 degree field of view. I have on loan from Peter Mack, unbelievably lenses, a Canon 200 millimeter f2 lens. The purchase price, I think, was around $25,000 when it was made. And that will give a 10 by 6.9 degree field of view of the sky with perfect stars all the way out. Then we've taken some pictures of the Sigma art lens and with a 135 millimeter and a 20 millimeter. And the next slide. So here's the Grasslands Observatory. You can see why we call it Grasslands. And this is the Earth's shadow at night. You can see the shadow of the Earth and the belt of Venus there above it. So getting ready for nights observing. Next slide. There's the old 24-inch telescope at the Grasslands Observatory. I used this for many years for photography at the Newtonian F5 focus. That worked pretty well, but the clock drive wasn't always the greatest. And when you have things way up the Newtonian focus, the weight and balance is always an issue. So when I retired a number of years ago, I just said, I'm going to spend money. This is an example of a hobby run amok. I'm just going to do remote imaging. The next slide. So here's the picture of my truck sitting next to the old building. And now I have a warm room, and we have on the left a storage room. This 35-foot pole there was necessary so I could get internet. Fortunately, the power company will put in poles for you. And then the three buildings there, the farthest building in the back is a 20-inch, the one that's closest is a 24-inch, and the one on the right is the Takahashi. And so those are off roofs, which I can run remotely. Now, advice to somebody, when you run things remotely from home, you have to be prepared to get in the car and drive down there in the middle of the night, in case, or you have to be prepared to have somebody be able to do that. So anytime you see some article about it, it's easier than pie. Remote thing is wonderful. I just go to bed, I get up in the morning, everything's been processed. I just send these away for publication. Well, it doesn't quite work that way. At least in my clumsy hands, it certainly doesn't work that way. We have the next slide. So I said the wide field image of the Canon. Generally, I use an EOS RA mirrorless full frame camera. It's really a nice camera. The Takahashi telescope, which is gorgeous, or the 200 millimeter lens, which I hope Peter McNair wants to take back. And next slide. So here's the Takahashi camera, or the telescope, and the camera's on the side with the guiding scope. Next slide. And here's the type of picture you would take with that. Here's a nice picture. Barnard 33, the Horsehead Nebula. Okay, we have the next slide. Here's the North American Nebula. Now look at this. And I've identified Barnard 358. It's a little small dark area. Barnard 355 is a really tiny dark area. Barnard 349 is over to the right of the Pelican Nebula. The Gulf of Mexico there doesn't have a Barnard object. It's got a lens later that described dark nebula. For whatever reason, he didn't want to bother to number that. And then at the very top, we have Barnard 353, and then above that, hidden off the slide actually, is Barnard 352. Next slide. So here's the thing. Here's a picture of what chart? Oh, I can't see that. I think this is chart 31. And you can see here's the picture of Barnard on the left. You can see he has 143 and 142, and there's his picture, the plate that he had. So let's take the next slide. Well, here's the wide angle picture of that. See that Barnard 143, that's so-called Barnard's E object. This is actually a nice visual object. And the little dark area down below that's sort of hidden by the text is Barnard 142. And this is with the Takahashi. This is about a 3 by 2 degree field of view. Next slide, please. Well, I can use the Finger Lakes KAF 9000 CCD, which is 3096 by 3096, 12 microns. So it's basically 30 millimeters by 30 millimeters, either with a plane wave telescope, which will give a field of view of 31 arc minutes, or the ASA 20-inch astrograph, which gives a field of view of about 70 minutes. And we have the next picture. So here's a telescope. That's a 20-inch telescope on the left and the 24-inch telescope on the right. On my website, kind of hidden, but you might want to look at it sometime. It's old, but there's an essay that ought to be updated of what can go wrong with your observatory. Next picture. This is that E with a 24-inch telescope. There again, if Barnard had images like this, you can see how that's filling in with dust. And one of the things he did notice when he took longer exposures, these areas would fill in. So he began to be suspicious that they were not holes in the sky, but they were actually dark obscuring matters. He actually tried to visually look at a lot of these. And a few of them, these theories, while they look dark on the photographs, are actually brighter than the background. He actually said some shimmering from them, knowing there was some emission coming off them, that they were matter, rather than just being dark holes in the sky. Next slide. Remember, in his day, they didn't understand what the Milky Way was, didn't understand the concept of galaxies. Here's a picture of Barnard 63, all kinds of Barnard objects in this field. So you can see Mary Calvert charted this, and then you can see his picture on the right. Very nice. All those dark areas show up. We have the next slide, please. So this is Barnard 63 with the Takahashi. There again, you can see when fairly long exposure, these areas will begin to fill in with star formation. So definitely not areas of holes in the sky. We have the next slide. This is the 200 millimeter f2 Canon lens. Yeah, priceless. Next slide. And here we put a piggyback on the 24-inch telescope. By the way, that telescope, that Meade LD 75, is actually a fairly nice 8-inch, 4-inch telescope. It's not as good as these others, but it's actually a fairly nice telescope. But the 24-inch telescope now, the old one, the original one, is now used at f20 for visual observing. Yeah, next slide. So this is a picture of, see that big area in the middle of the slide? That's Barnard 144. And on the top, you can see a little triangular shaped area. That's Barnard 145. So we have the next slide. So you can see his photographic plate on the left and my wide angle plate on the right. So you can see what color does. You can see all the emission nebula, red nebulosity in there, which really doesn't show up in his. We have the next slide. Barnard was very fascinated by star clouds in the Milky Way. So one of the things I did for this book is learn a little bit about the star clouds. I made some charts of them. And you can start out going north. Barnard did not describe this, but there's a dark area north of Cygnus called the funnel cloud. This has actually been known for a long time, but recently got the name funnel cloud. There's a dark area next to Denham called the northern coal sack. Then the area in Cygnus, which is a very prominent, is called the Cygnus star cloud. And then what Barnard was very fascinated, when we come down further south by the Scutum star cloud, he particularly fascinated by this small Sagittarius star cloud, which is M24, and the large Sagittarius star cloud. On the picture on the right shows a little bit better the small Sagittarius star cloud and the large Sagittarius star cloud. And where I have asterisks, you see a dark configuration, that's called the prancing horse or dark horse nebula. This is actually visible to the naked eye on a dark sky side. It's really a very nice thing. And that all that dark area there is made up of various Barnard objects. We have the next slide. So here's a more close-up view of at the top is a Scutum star cloud, SSC, that I labeled like LBN 70, M16, M17, the small Sagittarius star cloud. Then you can see the prancing horse nebula there, M22, M8, and large Sagittarius star cloud. And you can see over onto the right, Antares, and Barnard 44 is this long lanes of darkness that's north of Antares. The next slide. And here's the dark horse nebula with the 20-inch lens, the 20-inch, sorry. And you can see that curve, and I wish I had this slide, curved area near the top is Barnard 63, and about halfway down, a little toward the right of center, is a little snake-like area. That's called the Snake Nebula, Barnard 72. And then the dark area at the bottom is kind of partially hidden by the text is a combination of Barnard 78 and Barnard 59, 66, 67, and so on. We have the next slide, please. Okay, here's the Scutum star cloud. And this is Barnard's picture of it right there on the left. And this is a wide angle picture I took on the right. Okay. Does that show up? No, it doesn't show up very well, unfortunately. All right. Well, you can see anyway on Barnard's picture, you can see that area of bright emission nebulosity, the red area inside the dark V-shaped region. It does show up in this plate, but you can see, and you can right at the top up there, you can see the nebulosity, and that shows up in his plate. There's a fairly long exposure. So this plate's went long enough, they would show up as emission nebulosity. Oh, I'll try this one. Oops, sorry. This compared to that. And these are the dark areas here and here. And here they are, here and here. We have this here, that there. Okay, we have the next slide, please. So this is a close-up view of this, and you can see in the M24 area, you can see you have Barnard 304, Barnard 92, Barnard 93, Barnard 307, and this NGC 6603 is often in books mistaken for M24. It's actually the whole star clouds, what Messier described. And the next slide, please. And this is Barnard 92 and Barnard 93, close up. Next slide. One of the really nice things, and this is a beautiful object to look at, is Barnard 86. He saw this, stumbled across it when he was comet observing many years before he was at either Lick or Yerkes. And he thought this was a hole in the sky at the time. It's right in the middle of an extensive star cloud. Have the next slide, please. If you look at this with a 24-inch telescope, you can see it fills in somewhat. There's a nice little cluster right next to it. They're not associated. Here's Barnard's picture on his photographic plate that enlarged about the same scale. His plates were amazing resolution. When you consider that. This plate was probably taken about 1905, and this was taken a couple of years ago. This was taken with a 10-inch telescope. This was taken with a 24-inch telescope. Next slide, please. So Barnard photographic plates were very insensitive compared to modern films and digital imaging. I just sort of made up a number. They're roughly ASA or ISO 2 or less. They were sensitive to blue and actually were sensitive to ultraviolet light, amazingly enough. They're insensitive to green, insensitive to orange, and red. Next slide. This is another example. This is the region of Barnard 40. This is the 49th plate. This is IC 1396. I think I got that right. And there's all kinds of dark objects in this. And actually, Elephant Trunk Nebula is in here too, if you got it closer. Notice this bright red star. This is called Mu Cephei, or Herschel's garnet star. Next slide. So here's a blow-up of Barnard's plate, and there's that star. He didn't even notice that. I mean, he knew it was there, but he didn't bother to mark it. You can see how much it shows up in this, and how little it shows up there. And you can see all these dark areas here that you mark. I mean, there again, you see the numbering isn't totally consistent. We have 160, 162, 163. Then we have 305 here, 387. All right, next slide, please. So many Barnard objects are worthwhile for visual observing. I just point out a couple of them. A lot of them are stunning photographic delights. A lot of them, though, are challenging imaging targets. You basically can't see them, even with the biggest of telescopes. And it's kind of hard to distinguish in background sky, even on good photographic efforts. Yeah, the next slide, please. So the Astronomical League, interestingly enough, has a dark nebula observing program. You either photograph it or you can observe them. And I did this a number of years ago. You have to log or image 35 required objects, 26 of which are Barnard objects. You have to log or image 35 from a list of 102 other objects, the majority of which are Barnard objects. And on the Astronomical League list, which is really a very fine list, the objects vary in size from many degrees, like the Great Rift and from Cygnus to Centaurus, to Barnard 117, which is a small 2 by 1 arc-minute nebula. Have the next slide, please. So they never had Barnard objects 176 to 200. So I'm thinking, well, he marked areas that he never put a number on. I'm going to number them. And so Jerry Dobeck and I came up with missing Barnard objects. And we numbered from 176 to 200. We have the next one. So if you look at the plate on chart 13, this is here's Antares down here. And this is area of Barnard 41. And there's Barnard 44 here and Barnard 45. But he marked these areas here. So we decided to put numbers on them because obviously neither a nebula there. He hadn't gotten around the numbering. So I'm going to put a number on them. Jerry was fascinated by this here. I'll show you a picture of this. This is an area of dark nebulosity he called the trident because it looks like a trident. It's very small here, dark nebulosity. We have the next slide, please. So here's this picture of this area. So, and the things in red are the newly found Barnard objects. 177, 176. These you already knew. Antares is hidden by the text slide over here. And right down here is the trident. You can see it looks like a little trident. We have the next slide, please. And here it is closer up. Sort of looks like a trident, doesn't it? It was kind of an overprocessed slide. Here's Barnard 42. We have the next slide. So there are 380 Barnard objects total if you go by my counting. So his initial list was 182 objects. When they had the Atlas published in 1927, they added another 170 objects. And then we added another 28 objects. So there's 380. All right. Now you might not find that in Wikipedia. All right, we have the next slide, please. Barnard often used the terms dark nebulae, dark regions, dark zones, dark lanes, and dark markings interchangeably, which is very frustrating because in the literature, these terms are all used all over the place. We have the next slide, please. Common terms that are used interchangeably are dust cloud, molecular cloud, and dark nebula. They're often used interchangeably, which I find a little frustrating. Well, where are the Barnard objects today? Well, the same place they've always been. They're actually changing, but of course not in our time scale. But they're regions of intense study because they're looking for star formation. Dark nebulae are places, potential places of star formation. We have the next slide. Well, cosmic dust. I said, well, you know, what is cosmic dust? In fact, what is dust? It turns out ordinary dust is mostly follicles from skin, from pets, and from our skin, and little particles of dirt, and a little bit of minerals, like quartz minerals floating around the air, very tiny. So what is cosmic dust? Well, kind of hard to go out and get a sample, but it's presumably 1% of the interstellar medium in general is dust. It's composed of submicron size. The red blood cell is 7 microns in diameter, just to give you some perspective. So this would be, you know, a 1/7, 1/10 the size of a red blood cell. The silicates, like silicon dioxide, carbon compounds like carbon sulfide, graphite, just pure carbon, iron particles, aromatic hydrocarbons. These are hydrocarbon ring hydrocarbons, which may be, you know, ultimately precursors of amino acids and larger molecules. Ices, like I said, frozen ammonia, frozen water, frozen cyanogen gas, and other molecules. And the next slide. So cosmic dust absorbs visible light, especially at the blue end of the spectrum. So starlight shining through a dust cloud appears redder. And infrared, microwave, and radio waves are used in the modern study of the interstellar medium. And molecular clouds and dark areas like the Barnard objects. So if you go to the modern literature, you'll see the main literature on these things is from radio waves, microwaves, and some infrared. We have the next slide. So dark nebulae are mainly molecular hydrogen. They contain helium and carbon monoxide. The dust we just mentioned, they contain water, hydrocarbon, and many other molecules. A moderate-sized nebula that may be the site of solar or small-sized star formation. Tiny Bach globules may or may not be the site of star formation. If they are, they're going to be sun-sized or smaller. There's presumably one carbon monoxide molecule per 10,000 hydrogen molecules. But the carbon monoxide, molecules are studied by microwave emissions. So by studying where carbon monoxide is, you make the assumption that you have atomic hydrogen and molecular hydrogen. So that's how you study these star clouds as far as the composition. Very large nebulas can be the site of large mass star, phrase like O and B sized stars. We have the next slide. And currently this is in the midst of the book, and this has changed, but these right here are all areas of being studied, and they're either star formation or protostar formation in these Barnard objects. There are probably many others that are being studied. One of the big questions is, what is the distance of these? And it's very hard to know the distance of a dark nebula. You can get the distance of something behind it, but very often these are just silhouetted. They're often not associated. We have the next slide. So coming soon, I'm going to have the Barnard algorithm, another book. I am not going to bore you with talking another book, but I am going to bring copies of it to give out when it comes out. Next slide. So what I'm going to do in this book is I'm going to have a plate like plate 1, Barnard's plate. Next slide. I'm going to have a color image of the same area at the same scale, roughly. You can see some nebulosity. Oops, up there. Next slide. The next thing is going to have the chart that Barnard did, or Mary Calvert did. The next slide. I'm going to have things labeled on that. So it's sort of somewhat of a picture book. Now notice this up here, the next slide. And then I'm going to have pictures like that discussed. And this is also something he mentioned on that slide. This is NGC 663. So that book will do that for all 50 plates. Next slide. If you want to look at my work on the Barnard objects, you can go to the Grasslands Observatory. Next slide. So what some of Barnard objects are important from a historical point of view? I think a lot of them are arbitrary, and there are multiple dark areas. He didn't specifically catalog. I've already shown you examples of his irregularity in the numbering. but there are many of them are areas of intense study because they are regions of star formation or potential star formation. And the next slide, please. Oh, that's the end. Here's Nancy up here. Thank you.
We're going to open it up to questions. We've got a lot still ahead of us tonight, so we're not going to do a lot of questions. Maybe 3 or 4 here, then we'll go to some of the online sources as well for questions. So we got folks who are going to be coming around with microphones. So if you have a question, wait till they get to you before you answer it. Opening it up. Well, they'll make it easy, keep it short. Way up there. Gonna make Terry work. I do want to say I loved all the references to Yerkes Observatory. I grew up spending my summers at my grandparents' cottage just down the lake from Yerkes, and I almost in the shadow. So that
Oh,
I
wow.
love that.
Lake Geneva.
Yeah.
Well, thank you very much for the really great talk, and especially all the amazing photographs that you showed in the talk today. I had a question about the history and Max Wolf and E. Barnard, and in your study of that history, have you come across any indication, like maybe which one had the idea that these weren't vacancies or voids and they really were dark clouds? Have you come across like a reference that predates the other one?
You know, I can't really, I got a feeling that Barnard did a lot more than Max Wolf did. So I got a feeling it was Barnard. And Barnard has a very interesting article that in 1913, he was actually out photographing. He was at Yerkes Observatory. And this shows how light pollution was nothing in those days. He noticed that when very tiny small clouds had gone from the Milky Way, how dark they were. And that's when he realized that this was dark stuff in front of it. Nowadays, if you have a cloud that would go in front of something, cloud would be brighter than the Milky Way. But in those days, it was so dark there. So from about 1913 on, he did. I haven't found anything that Max Wolf said, but he was certainly a contemporary. Max Wolf was incredibly distressed when Barnard died. Wolf outlived him by about 10 years.
Anybody else? Right down here, Terry.
Thank you very much. It was absolutely fascinating. What is your favorite object of his?
Barnard 86.
Oh, yeah.
And what is the name of that? Do you know, or is it just the catalog name? Or?
The hole in the sky.
Is that the one with the bright star right?
Yeah, right.
to it in the-
It's right. It's the one that's a dark thing, and it's got a little bit of it's a thing. It's a very nice telescopic object. I'm not the greatest visual observer in the world, and this is one I can see.
I think it's easy to find as you go from Lagoon Nebula, like straight north or something like that. I can't remember. It's been a while. Anybody else?
Jim, what do you got online there from Zoom?
Not much for questions, but Matthew Oda shared quite a few pictures of some of the observatories and of the people. And he says Barnard's Wooden Observatory, Mount Wilson Observatory is one he shared. He said he used to work next to the remnants of Barnard's Observatory of Mount Wilson. And then just lots of great talk, but no specific questions.
Tim, thank you.
I
Always
have one.
pleasure. I'm sorry?
I have one from
Oh,
YouTube.
I'm sorry. Yeah, we got
Okay.
YouTube.
Yeah, Nadia from you on YouTube says, is it known how he decided which objects to catalog? It seems like there are more obvious holes close to many of his objects.
No, what frustrated me, he never listed what his criteria were for cataloging these things. And in fact, there's a density thing that's given to him that Beverly Lynn, who just recently passed away as an astronomer, she was at university at one time. She did a catalog of these things from them that she derived from the Palomar Sky survey plates of both dark and bright objects. And she had a thing from 1 to 6, where 1, they weren't very dark, the 6 are very dark. Barnard never had any. He never had any criteria for size, didn't have any criteria for numbering that I could see, any criteria why he did it or not. I think what happens is he was so busy with so many projects, he would scurry from one thing to the other. He'd put these aside, then come back to it. Couldn't quite remember where he was before. That's what I surmised, but I can't tell. And I've asked his biographer, Bill Sheehan, he didn't have any clue either.
Last chance, everybody. Always a pleasure to have Tim speak to us.
Okay. Mhm.
And we're going to be wrapping off 5 of his books. Terry, how are we going to be doing this? So we're going to say goodbye to our YouTube folks out there and bring the rest of this into the membership. So thank you for the public out there on YouTube. Thanks.